Okay, welcome back everyone. This is Dr. Goldstein. Today we are going to do an application of the kind of modeling that we've been developing. So far in the course, we have talked about how to represent the decision-making process and the preferences of rational agents. If you remember, we explained that the preferences of rational agents can be kind of captured or mathematically expressed in the form of a utility function. And then we talked about how the decision-making process of rational agents can be modeled using a utility maximization process, subject to some constraint. Okay, so what we've done is we've built the basic toolkit, the basic framework to mathematically express and mathematically model human decision making. We can use these models. We can use these models for very important purposes. So we can use these models. We can use these models to one. We can do kind of some kind of predictive policy analysis. We can kind of try to predict what policy or interventions might have based on a mathematical model of human decision making and human behavior. So we can predict policy analysis. We can generate. We can generate predictions and or hypotheses. We generate predictions or hypotheses that we will test using data. So we can test these hypotheses using data. We can test them using our impact assessments if, say, we are looking at the impact of some sort of development program or policy. Okay, so that's kind of what we use this for. You know, if we're writing a research paper, we will use a theoretical model to generate predictions, and then we can test those predictions. Empirically. Okay, so that's kind of what we're doing. We're building that skill set that's going to allow us to generate models. Well, what I want to do today is I want to develop a model of decision making of a representative household, let's say, and just kind of illustrate how these models might be helpful for us in terms of generating predictions that can be tested empirically. Okay, so let's do that. What I'm going to do today is we're going to look at, I'm just going to call it household investment decision making. It's going to be a very simple model. Okay, but I think the model is going to give us an opportunity to get some insights into how these mathematical models can be helpful to us and how we can use them to model decision making. Okay, so that's what we're going to do. We're going to look at household investment decision making. This also carries over into the overall purpose of the course, where one of the purposes of the course is to understand advanced microeconomic thinking, but then to go beyond that, we want to apply it to tangible questions that are particularly important in the development economics context. All right. And so we want to kind of build the toolkit to be complete economists, complete development economists. So that's what we want to do. So this model that we're going to look at today is going to give us the opportunity to kind of think about some policies that might be relevant to us in a developing country context. Okay, so let's just jump right in. First, I just want to give some background. Why am I looking at household investment decision making? Well, I'm going to conflate some things for the moment. Savings and investment is critical for economic development. It's critical for economic development and personal or household development. All right, it's critical for economic development and household development. So, in terms at the national level or the economy-wide level, savings is an important driver of economic growth. Because when households save, then the financial market has the resources necessary to offer loans that can be invested in the accumulation of capital, which can over time improve productivity and result in overall economic growth. So savings and investment are really important for economic development. And of course, they're important at the personal and household level for pretty much the same reason. You know, if a household is saving money, then they can use that money to invest in maybe in starting a new business or to invest in new assets for their business. Or they can, invest it like we would think in the United States, invest it in the stock market and grow their wealth over time. And so savings and investments are critical for a household to grow out of poverty, whether you're in a developed or developing country context. And so this is a really important topic in the world of economic development. And especially from a microeconomic perspective, we're very concerned with individual level or household level decision making as it relates to investments. We want to know what are the factors that influence investment decision making so that we could potentially design policy or design interventions that might help to promote investment, because promoting savings and investment can help lead to the alleviation of poverty. So that's what I want to do. And so we're going to do a simple model of that today. All right, so there's the motivation. Let's jump right in to the model. Now, first, before we model this, we need to build a toolkit. We're going to build a toolkit. We got to explain a couple concepts. All right, the first concept is I want to explain what I might call an intertemporal or a dynamic utility function. Okay, so this is kind of the first thing that we need to include here. So let's go into it. So investment decisions are fundamentally dynamic. All right, so investment decisions are dynamic. What does that mean? What do I mean when I use the word dynamic? What do I mean? What I mean by that is it involves time. It involves time. Or things change over time. And so what I mean by that is that I make a decision in the present, and it has consequences for me in the present, and it has consequences for me in the future. And so when I make a decision today, so I make a decision in the present, this decision will affect me today, and it'll affect me in the future. And so when I am making this decision, I need to think about the present, and then I also need to think about the future. So when I'm thinking about investment decisions, I have to consider both the present and the future when I make that decision. That means that my model has to capture the present and the future. My model has to capture how my current decision making will affect me today and tomorrow and the next day and the next day and the next day. Well, that's what I want to do when I develop or when I use a dynamic utility function. I want a utility function that's going to capture the present and the future. I want to capture things as they change over time. All right, so let me just write a very, very simple example of this, and that's what we'll use in the class. So imagine I'm going to have a function, I'm going to call it capital U. It's going to be a function of consumption today, which I represent by C1, and consumption tomorrow, okay? So C1, consumption today. C2, consumption, let's just say in the future. All right, this is kind of abstract, All right. U, this is a function. What it does is it gives me the net present value of current and future utility. So this is a function that basically is going to give me, it's going to account in present terms both the utility I get today and the utility that I will get in the future. So this is how I'm going to write this. I'm going to say utility that I get today as a function of consumption today, plus the utility that I get tomorrow as a function of what I consume tomorrow. Okay, so this is current consumption. So this is present consumption. This whole term is present utility. Present utility. Okay. This whole term here is future utility in the abstract, future utility. And C2 is future consumption. Okay, so here is it's a utility function. This whole thing here is a utility function that accounts for the present, and the future. Okay, so we have a utility function that accounts for the present and the future. All right, so that's the first toolkit. We need to have that. What's the second component of the toolkit? Second component, actually, let's see, I'm just going to write our utility function up here. C1, C2 equals U of C1 plus U of C2. Okay, so here's our utility function. Second tool, our second tool is going to be discounting, or the discount factor. All right, so let me explain this. So whenever we think about decisions dynamically, we always have to consider, again, the present and the future. But humans don't think about the present the same way they think about the future. Typically, humans put greater value on the present than they do on the future. And we can think of all kinds of reasons for this, but a simple reason would be that today, I know I will have my current consumption, but I don't know if my future will come. And so I'm going to put less value on future consumption, on future utility, than I do on present utility. Okay, well, how do we account for that? We account for that by using something that's called a discount factor, which we represent typically with the lowercase Greek letter delta. The discount factor, delta, is a number that is bounded between 0 and 1, and we multiply future utility by delta. And so the idea here is that, again, this term captures the present, this term captures the future. And let me be even more specific. This term here captures the present value. That means the value in the present moment that I give to my present utility. So the present value of current utility. Okay, this term here corresponds to the present value of future utility. All right, present value, that means the amount of value that I put on, the amount of value that I put today on the utility that I will receive in the future. And so to account for the fact that this utility is in the future, I multiply it by delta, which is a number, again, between 0 and 1, which means that I put less weight on the future than I do on the present. If delta is equal to 0, that means I don't care about the future at all. I don't care about the future. If delta equals 1, that means I care about the future as much as I care about the present. I care about the future as much as the present. So if delta equals 0, that means I don't care about the future. If delta equals 1, I care about the future as much as the present. And if it's anywhere in between, so if delta is greater than 0 and less than 1, if it's anywhere in between, that means that I care about the future less. I put less weight on the future than I do the present. I put less weight on future utility than I do on the present. That means my present value, the present value, that means today, how much weight I put on my future utility is smaller than the amount of weight that I put on my present utility. All right, so this is overall, let's just clear this. Let's clear this and summarize. This is going to be my dynamic utility function, okay? It is the present value of current consumption plus the discounted, so plus the present value of discounted future consumption. Okay, so here we go. This is my dynamic utility function. I'm going to use this to capture, to try to model decision making where the present and the future matter to my decision making process. All right, boom, done. That's the framework. There's the toolkit. Let's start with our model of investment decision making. So our model of, in this case, we can call it investment or we can call it savings. Okay, so what we want to do is we want to model, let's do this. Model of savings. All right, so let's get this thing started. So we're going to build a model. Okay, we want to look at savings behavior. So we're gonna have a variable s called savings. This is going to be our variable. It accounts for an action that we're interested in. We want to study this behavior, action or behavior. We want to know how much do people save. Okay, so we have a variable savings. All right, we want to account for this over time. So we know that we're going to have a utility maximization process. It means we want to know how much is people going to save. Well, how do rational agents make decisions? They choose the variable in order to maximize their utility. So we know that we're going to maximize some utility function with respect to savings. All right, so we know we're going to get here somehow. Somehow we're going to get here. We're going to build a model where we have this, and then we're going to solve this utility maximization problem. Okay. Well, how do we do this? Well, first we need to recognize our utility function is dynamic. So let's set up a utility function just like the one we did before. All right, so utility of consumption in year 1 plus discounted utility of consumption in the future. Okay, and then let's define what consumption would be as a function of savings. And so let's say C1, that means the amount that I consume today. Simplest model here is just my income minus how much money I save. And then how much do I consume in the future? Well, let's just say this. It's income plus the amount of money I save times my return on that savings, where rho here is the gross interest rate, aka equals 1 plus r, where r is the interest rate. Okay, and so if the interest rate is positive, so let's say I put my money in a savings account in a bank, and the savings account offers an interest rate, and it's a positive interest rate, then my savings will grow over time. So basically what's happening here, so we have this dynamic process where in the present, agents are making a decision as to how much to save. the more that they save, the less that they can consume in the present. Okay, and then in the future, they get to save their saving. I'm sorry. In the future, they get to spend their savings. They get to spend their savings, plus any return on that savings. Okay, so then these are the consumptive decisions. We want to. We have just this very simple framework that tries to capture the fundamental features of savings behavior. The fundamental features is that I make a decision in the present. I make a decision in the present regarding how much to save, and this decision will decrease consumption today in order to increase consumption tomorrow. Okay, so we've kind of captures these essential features. So then how do we model this? How do we model the decision making? So we have the setup here. Now we want to set up a maximization problem so that we can study the decision making process. How much are they going to save? Well, how do we model decision making? Well, we model it as a utility maximization process. So we want to maximize utility. We want to choose a value. We want to choose the amount of savings that will maximize the utility, and that is maximize the present value of current consumption and discounted future consumption. Where C1 is equal to I minus S and C2 is equal to I plus rho S. All right. Now we might impose a constraint. There is a constraint here. If we think about, well, what can this constraint be? Well, we might say that people cannot save more than their income, so their income has to be greater than or equal to savings. But if they were to save all of their income, then you would have consumption of 0 in the present, and people are probably not going to consume 0 in the present. So we can actually just ignore this constraint. So basically, here we go. Here is our utility maximization problem. So if we want to study savings behavior, here we go. This is what we need. We want to know how much are they going to save? Well, let's set up the maximization problem. That's how we modeled the decision making of rational agents. And we're going to solve this thing for S star. We want to find S star. S star is the optimal savings. It's the optimal savings, aka what the agent chooses. So if we solve for S star, we can derive some insights as to the factors that affect the savings decision. So let's do that. Let's solve this out. And as we're solving this out, I'm going to solve it out in a couple different ways. I'm going to be very methodical. I'm going to go step by step. And in that process, we're going to try to gain some deeper economic insight as I go through the process. Okay, so let's solve this out. How do we solve this? Well, we solve it by first setting up the first order condition. So we've done this before, so it's pretty straightforward. We take the derivative of the objective function. Okay, so here's the objective function. We take the derivative of the objective function with respect to the variable. All right, so let's do that. And then we're going to set it equal to 0, right? So if we want to take the derivative of this with respect to s, we'll go term by term. We'll go term by term and take the derivative. So then what's the derivative of this first term? Well, we have to apply the chain rule here. We have an outer function and an inner function. The outer function, the outer function is the u, the inner function is c1. c1 is a function of s, as you can see over here. So let's take the chain rule. Derivative of u with respect to c1 times the derivative of c1 with respect to s. Therefore, we have taken the derivative of the first term. It's this whole thing. Okay, so next we want to take the derivative of this term. So let's do that. Plus delta derivative of u with respect to c2. Again, we're just using the chain rule. Times the derivative of c2 with respect to s. Okay, so here we have the derivative of the second term using the chain rule. All right, and then we're going to take it and set it equal to 0. All right, so that gives us our first order condition. Now here at this stage I'm going to pause for a second and try to explain some things using some economic theory. So we know that S star solves the FOC. That means if we knew what all these functions were and we plugged them all in and we solved this equation for S, that would give us S star. S star solves the FOC. So then the FOC is going to give us a really interesting opportunity to understand decision making, and I think we'll find this intuitive and clarifying as to the decision making process of rational agents. So let's take a look. We know from the first lecture the equimarginal principle. Principle. The equimarginal principle. The equimarginal principle means that people choose optimal decisions. They choose optimal decisions on the margin, right? They choose optimal decisions on the margin. That means they're making decisions about marginal units, and they make the decision such that the marginal benefit of a possible decision equals the marginal cost. All right, so they make decisions such that the marginal benefit will equal the marginal cost. If the marginal benefit of an additional unit of savings, all right, actually, let me just clarify here. On the margin means we're always thinking about the marginal kind of unit of whatever good we're talking about. So in this case, it's savings. So when I say they make decisions on the margin, that means they're making decisions about marginal increments of savings. They're choosing between, will I save one more unit of my income? Am I going to save one more dollar? All right, they're making decisions about that marginal unit, that one more dollar. Will I save one more dollar? Will I save one less dollar? And they make decisions on that marginal unit, where they look at that one marginal unit, that one marginal dollar. Do I save one more dollar? And when we ask ourselves that question, do I save one more dollar? We look at the marginal benefit and the marginal cost of that one more dollar. I will save one more dollar if the benefit that I get from saving that $1 is greater than or equal to the marginal cost, or the cost of saving that one more dollar. If the cost of saving that one more dollar is larger than the benefit of saving that one more dollar, then I will not save it. Okay, so that's how people make decisions. People make decisions such that, so the optimal decision, that means S star is selected such that the marginal benefit equals the marginal cost. So for this S star, the optimal amount of savings, at that optimal amount of savings, the marginal benefit of that one more dollar of savings is equal to the marginal cost of that one more dollar of savings. All right, what does that mean mathematically? What does that mean mathematically? Let's take a look at what that means mathematically. All right, and we're going to see that all these equations capture this fundamental intuition about the decision making of rational agents. Okay, so let's take a look. What we're going to do here is we are going to go through each term here, and we're going to give it a sign. That means we're going to say whether it's positive or negative. And by doing that, we're going to see what is an expression for the marginal benefit and the marginal cost, okay, of the savings decision. All right, so hopefully this becomes clear. Let's go through this. The derivative of utility with respect to consumption 1, is this positive or negative? And what I mean by that is, if consumption in period 1, if consumption today goes up, will utility go up or down? If an increase in consumption causes an increase in utility, then it's positive. If an increase in consumption causes a decrease in utility, then the derivative is negative. So which one is it? It's positive. Okay, how does consumption 1 change given a change in savings? That means if I save one more dollar, will my consumption in period 1 go up or down? Well, I can get some insights by looking at the function. If I increase my savings, the amount that I consume goes down, so the derivative here is negative. I go to the next term. Delta is always positive or 0, but we're going to assume that it's positive here. All right, so it's positive. All right, again, how does utility change given a change in consumption? Well, if consumption in the future goes up, my utility will go up, so that's positive. We always know that the derivative of a utility function with respect to consumption is positive, right? That's one of the features of a utility function. It's an increasing function, right? Okay, now how does consumption in the future change given a change in savings? Well, let's look at it. If savings goes up, then consumption in the future goes up, because in the future we will consume, we'll spend the money that we saved. So then this is positive. All right, so if we look at this, we can see, if we look at this, let's do this. If we look at this, we can see that this whole term here is negative, and this whole term here is positive. This indicates to us that this is the marginal benefit. The marginal benefit of one, so okay, it's the marginal benefit, which means it is the benefit of one more dollar of savings. It's a marginal benefit of savings. This negative is the marginal cost, which means it is the cost of one more dollar. All right, now I said before, that S star, the optimal S, is the one that solves this equation. Well, look at how this works. This term is the marginal benefit. This term is the marginal cost. Let's take the marginal cost to the other side. I'm just going to rewrite this. All right, I'm going to rewrite this expression here. I'm going to write the marginal benefit on one side, and I set it equal to the marginal cost. And what we're going to find is that the optimal S, this is the level of S such that the marginal benefit equals the marginal cost. So the optimal level of savings is the amount of savings that equates the marginal benefit and the marginal cost. So basically, that fundamental economic intuition about the decision-making of rational agents is captured right here in the math. And this allows us to gain insights into the decision-making process. Okay, so now what I want to do is let's dig into this equation. I want to dig into this equimarginal equation here. I want to dig into it and I want to unpack it and try to understand, well, why is this the marginal benefit and why is this the marginal cost? So let's do that. I'm going to erase this and then we're going to rewrite it so we have some more space. Okay. So what we have here is we have the marginal benefit equals the marginal cost. Whoops. So this is 2. This is 2. This is 1. All right, so the marginal benefit equals the marginal cost. So the marginal benefit equals the marginal cost, and the optimal S is the value of S such that this is true. So the optimal S, so S star, the optimal S, the decision that people make is they will choose the value of S. They will choose the amount of savings such that the marginal benefit equals the marginal cost. Let's take a look at this. What is the marginal benefit? The marginal benefit of savings is that my utility in the future will increase. The marginal benefit of an additional unit of saving is that in the future, my consumption goes up. And because my consumption goes up, my utility in the future goes up. So more savings implies more future consumption, which implies more future utility. So the marginal benefit is all of the benefit, all the value that I get from consuming in the future. The marginal cost is what I lose in the present. So the marginal cost is the more I save, if I save $1 more, I consume less today. And if I consume less today, then overall I will experience less utility today. All right, so more S implies less current consumption, which implies lower current utility. All right, so the marginal benefit of savings is I get more in the future, and the marginal cost is that I get less utility in the present. And so I will save more if the marginal benefit of additional savings outweighs the cost. So if the benefit I get from future utility outweighs the cost of lost utility today, then I will save more. All right, so that's the fundamental decision-making process. And I will keep saving, I'll keep saving more and more and more and more and more until the marginal benefit of increased future utility is equal to the marginal cost of decreased present utility. All right, so that is the decision-making process of a rational agent regarding savings. That fundamental trade-off between what I gain in the future versus what I lose today is going to be the fundamental decision-making factor between choosing savings and investment versus choosing, so more or less of savings and investment. Okay, with all of that said, now I want to go a little bit deeper. So let me go a little bit deeper here. All right, so going into how we solve this model, so we choose S to maximize consumption, to maximize utility of present and future consumption, all right, where consumption today equals I minus S, and consumption tomorrow equals I plus rho S. Okay. Well, so we solved that out. We got our first order condition. I want to do something, again, what I want to do here is I want to go into some greater detail. I want to take these and I want to plug them in. And we'll get some greater detail into what this looks like. So let's plug this in and then solve it again. Max S U of I minus S plus delta U I plus rho S. All right, so now I'm going to solve it again. First order condition. The derivative of u with respect to c1 times the derivative of c1, that means the derivative of the inner function, which is just -1 times -1. And so we can rewrite that as just negative derivative of u with respect to c1, plus, take the derivative here, delta derivative of u with respect to c2 times the derivative of the inner function, which is just rho. All right, and then I'll rewrite this in a way that just looks a little bit cleaner. Okay, so now again, here we have this equal marginal principle, this first order condition. We can set the marginal benefit equal to the marginal cost. Okay. Marginal benefit is that utility in the future goes up. If consumption goes up, consumption will go up for each additional unit of okay, here we go. For each additional unit of savings, my future consumption goes up by rho. For each additional, so on the margin, each additional unit of savings will give me rho more income in the future, more consumption, and such an increase in consumption will increase my utility. So there's my marginal benefit. The marginal cost is that each additional unit of savings today decreases my consumption today by 1. And so that will give me a cost. That will cost me the utility that I would get from consumption today. So here's the marginal cost. Okay. Okay, so there we go. Now, what I want to do next is I want to do the same problem, but now I want to define my utility function as the natural log utility function so we can get some more precise estimates and do some more precise analysis. So let's do this. We're going to choose savings to maximize utility. All right, so here's our new utility function. Our utility function now has the natural log instead of just the generic u. So let's solve this for S star. Okay, the derivative, all right, so it's just 1 over I minus S. That's the derivative of the outer function, times the derivative of the inner function, that's -1. Okay, derivative of the outer function is delta over I plus rho S times the derivative of the inner function, which is just rho, equals 0. All right, just going to rewrite this, -1 over I minus S plus delta rho over I plus rho S equals 0. Okay, so let's solve this out. I'm going to take this term. I'm going to take this term to the other side. So we're going to get delta rho S, okay, equals 1 over I minus S. I'm going to cross multiply. That means I'm going to multiply both sides by I plus rho S. So that would cancel out over here. And I'm going to multiply both sides by I minus S. All right, so that's going to give me delta rho times I minus S equals I plus rho s. My goal, remember, is that I'm trying to solve this thing for s. I'm going to distribute this. I want to get s alone. Okay, delta rho I minus delta rho s equals I plus rho s. All right, I'm going to consolidate all the s terms. I'm going to consolidate all of the s terms on this side of the equation. Actually, I'm going to do it backwards. I'm going to consolidate all the s terms on this side of the equation and all of the I terms on this side of the equation. So I'll have delta rho I minus I equals rho s plus delta rho s. Okay, I'm going to factor out. I'm going to factor out the I. And I'm going to factor out the s in the row. I'm going to factor out the s in the row here. Sorry if that's unclear. I delta rho minus 1 equals s rho 1 plus delta. Okay, and I'm just going to switch sides so that I have s on the left side. It's just kind of a matter of preference. Oh wait, whoops. S, okay. So I'm going to have s rho 1 plus delta equals I rho delta rho minus 1. Then I'm going to solve this for s, and we're going to get s star. S star equals I over delta rho minus 1 divided by rho 1 plus delta. So here we go. This is my s star. Here's my s star. This is the optimal decision. This is the optimal savings decision as a function of the parameters of the model. So if we knew all the parameters, that means if we knew income, we knew their discount factor, and we knew the return on savings, we would be able to say how much they would save in this model. Optimal savings decision. Now what makes this interesting, what makes this whole process interesting is that we're going to be able to take this and we're going to be able to derive some predictions about how, so this is where it gets really interesting, we're going to be able to derive predictions as to how changes in the parameters affect optimal savings. Why is that interesting? Well, it's because we can design policies or interventions that target the parameters. We can target these with policies. So I want to know, basically this is what I want to know. I want to know, how does a change in income affect savings? How does a change in the discount factor affect savings? And I want to know, how does a change in the return on savings affect savings? I want to know these three things. All right, so let's do that next. All right, erase everything. Now we're going to do our policy analysis here. Okay, so we have S star. This is how much that they are going to save, and we're going to do some analysis on it. We're going to generate some predictions. So if we want to increase savings, that means we want to know what are the factors that would increase savings. Well, let's take a look. Let's do it one by one. Derivative of S with respect to I. How does an increase in income affect savings? Now, we might be able to intuit it. Again, this is a very simple model, but let's just do it mathematically. What is the derivative of this with respect to I? Well, if we think about this as delta rho minus 1 over rho 1 plus delta times I, then the derivative becomes straightforward. It's just delta, actually I don't even need the parentheses anymore, delta rho minus 1 over rho times 1 plus delta. So now the question is, how does a change in income affect savings? Well, it affects it in this way. So really the question we want to ask ourselves, is this number positive or negative? That's what we want to ask ourselves. Is this number positive or negative? Well, you can see that in a sense, it's a little bit ambiguous. If delta rho minus 1 is negative, then an increase in income would reduce savings. But let's assume for now that delta times rho minus 1 is positive. If that's the case, then this is positive, which would imply an increase in income will increase savings. So here is an implication of our model. It's a prediction, and we could design policy on this. We could design policy based on this. So if we want to increase savings, design policies to increase incomes. So we can say this is like a hypothesis or a prediction. And here is a policy. All right, let's do the next one. Derivative of S with respect to rho. How does an increase in the return to savings affect savings? This is a little bit more of a complicated derivative, unfortunately, because this is the quotient rule. So bear with me here for a second. We're going to do this derivative, and it's going to kind of be ugly. Remember the quotient rule. I'll just write it up here in the corner. The quotient rule is, imagine that you have g of x divided by h of x. The derivative is g of x, g prime of x times h of x minus, running out of space here. Actually, I'm running out of space. Okay. So if you have a function g of x divided by h of x, the derivative would be g prime of x, h of x, minus g of x, h prime of x, all divided by h of x squared. So let's apply the quotient rule and do this derivative. Okay, here we go. G prime of x. Derivative of the top with respect to rho, that will be I delta times the bottom, rho 1 plus delta. Okay, minus the top, so that's I times delta rho minus 1 times the derivative of the bottom, which is 1 plus delta, divided by the derivative, or the denominator squared. Okay, this is a little bit ugly. Let's simplify it. If we simplify it, it will allow us to see what the sign of this is, which is what we want to know. So let's simplify it. To simplify it, I'm going to distribute everything, which is a little bit cumbersome. First thing I'm going to do is I'm going to factor out the 1 plus delta. In fact, I'm going to factor out I times 1 plus delta because that is the same in both of these terms. So I'm going to do that first. I, 1 plus delta, okay, and then everything else. Delta rho minus delta rho minus 1, okay? And then in the denominator, it's rho squared 1 plus delta squared. Well, this gets a little bit easier because we're going to notice that this 1 plus delta cancels out with the squared term, so we're going to get rid of that. Let's come down here again. Now we have I. The numerator will distribute this negative term, so it'll be this minus delta rho plus 1. all right, divided by rho squared 1 plus delta. So now this is pretty straightforward. These cancel out, and this simplifies to something pretty easy. I over rho squared 1 plus delta. All right, so how does a change in the return to savings affect income? Well, if you look at this, you will see that this is a positive number. Income is positive, rho is positive, delta is positive, so all these numbers are positive. That means that this is positive, and if this is positive, then it has an implication. Hypothesis: an increase in return to savings increases savings. Okay, so then the policy is design policy to increase returns to savings. Okay. Okay, I'm gonna erase some of this here. Give ourselves some more room. Okay. All right. Last one. How does a change in the discount factor affect savings? Well, again, we need to use the quotient rule. So let's do that. I rho, all right, so the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Okay. And we will simplify and factor some things out. So let's do that. We'll factor out I, we'll factor out rho. Okay, so then we have rho 1 plus delta minus delta rho minus 1. Okay. And then we have rho squared 1 plus delta squared. Okay, so let's simplify the inside. I rho. We'll distribute everything inside, so it'll be rho plus rho delta minus delta rho plus 1 divided by rho squared 1 plus delta squared. Okay, these two cancel out. And so what do we get? We get I rho times rho plus 1 over rho squared 1 plus delta squared. We can cancel out one of these rows, and we'll get our final answer. I times rho plus 1 divided by rho times 1 plus delta squared. All right, so that's our final answer. Is that number positive or negative? Is that number positive or negative? Well, all these numbers are positive. Income's positive, rho's positive, delta's positive, so this is positive. That means if we could somehow design a policy to increase the importance that people place on the future. So we can somehow increase the importance that people place on the future. We will increase incomes or increase savings. Because an increase in the discount factor will increase savings. Okay, so there we go. What we've done is we have identified optimal savings behavior. We've then looked at how changes in the parameters affect optimal savings behavior, used that to drive hypotheses and policies that we think we could use to affect or improve savings. I keep saying incomes. Savings. Okay, so how is this a powerful tool? Well, it's powerful because it allows us to generate predictions and then predict policies that we could use to help achieve the development goals that we're seeking. Okay, so we're very interested now. So, okay, let's design some policies that will increase incomes. Oh, you know what? No, I did do this right. The idea is that we want to increase incomes because increasing incomes will increase savings. Okay. Now, in a very simple model like this, some of them are obvious. Like you might be looking at this and saying, well, I can just think about it. I don't have to solve a whole bunch of complicated math to figure out that increasing incomes is probably going to increase savings. And I don't need to solve a whole bunch of complicated math to know that increasing the returns to savings is going to increase savings. Okay, that's fine. But as models get more complicated, we're able to derive predictions that are much more difficult to come up with using just conceptual intuition. And I think an example of that might be this one. If you were to just sit down and try to think of the things that would affect savings, you might miss this one. But this one might be the most important. It might be hard to just exogenously increase people's incomes. But if you worked with people, if you conducted a staged field experiment, you might be able to affect the way that people perceive and weigh and value the present versus the future. This might be a really fruitful grounds to help improve savings behavior by looking at this last one. And this one might have been a harder one to come up with just based on basic intuition. Okay, so that's it for today. I hope this was a helpful and interesting illustration. On your homework, you're going to have to do a similar thing. On your homework, you're going to have to look at the decision of parents to send their children to school. And what you'll find is that decision-making process involves some of the same components because parents are deciding between basically investing in their children's education. And investing in their children's education is kind of like savings because in the present, you lose out on the income that your children would generate, but in the future you gain the benefit of your children having achieved an education and all of the benefits that come from that education. So you'll have to develop a model and look at the factors that affect whether or not a household will send their children to school or not. And you're going to have to come up with some policies that you might recommend to help improve school enrollment. Well, that's it for today. I hope you have a great day.